We're looking at Signal today, in particular Signal Android, which is the Android app of Signal. Signal is if you haven't heard of it, it's a popular encrypted chat messenger. It's famous, maybe most famous for its double ratchet algorithm, which has, since Signal has been built into a number of other pieces of software, chat systems, some of which are just everyday things like Skype. I think Google built it into some stuff. So one, I want to make sure we look at the double ratchet algorithm just to see a little bit of its implementation. I don't think we're going to understand the cryptography from the Android source code, although maybe we will. And then since this is, I think, the first Android app that we've looked at so far, it makes sense to look a little bit at the UI and the underlying stuff for folks who haven't had a chance yet to build a mobile app. And I think mobile chat apps are like one of the, alongside to do apps, are like a tried and true way to test your development skills. So I just did a search for ratchet because the Signal algorithm is called the double ratchet. So I figured this will show us where some of the cool cryptography stuff is, and we'll just kind of dive in there. Hello. What about UI? Oh, we're gonna see UI. Okay, so let's dig in first to the ratchet stuff, because I have a feeling that a lot of people who click on this video, that will be one of the first things they want to see. So here's message content processor.kt. And somewhere we had ratchet. Let me reopen this so that we get exactly to where ratchet is. Okay, so this we're in the function. This is Kotlin, for those who are not in the know. We are in the function handle individual retry receipt. Retry receipt. So I'm not sure if this is just retrying the receipt or retrying the message with receipt, but we're going to first check if decryption error message ratchet key is present. We're going to do some warning stuff. And where did the other ratchet thing go? Here, ratchet key matches. This is what I wanted. And I wanted it in a new tab. Thank you, though. Okay, so we have this message content processor.kt. We have this ratchet key matches, which we're going to get. We're going to give it a recipient, a device ID. I'm not sure exactly where the device ID comes from, but maybe we'll take a look at that. And then the ratchet key, which is going to be an EC public key. EC standing for almost certainly elliptic curve. So this is some elliptic curve public key. We're going to return a Boolean. And the first thing we do is we take the recipient and we try to resolve it. What does resolve mean? I'm not sure what it means. And we're going to require ACI. What is ACI? I'm not sure. And we're going to take the recipient and translate it to a protocol address, passing in the device ID. Is this my device ID or the recipient's? I'm not sure. Presumably the recipient's, but this is going to give us an address, which should essentially be where do we send it? And then in application dependencies, which I'm going to guess is we're sort of doing dependency injection. This is maybe just some global repo of all the dependencies so that we can get them from any class. We're going to get the protocol store, which should be just some, again, some global that we're peeking into that has protocol stuff, whatever ACI is, and load the session associated with this address. And then we're going to ask whether the current ratchet key matches the ratchet key from the session. Device is a MAC address. It says get study learn op. Okay, cool. Let's verify that in a little bit. And hello, Doraj. I am well. I hope all of you are well. Okay, so this is just checking whether two keys match. What else can we do? So maybe let's jump into. We don't have a lot of ratchet things. Maybe it's not called ratchet in the source code. Maybe it's called. Let's maybe just look for crypto. Crypto util. This is promising. No, I want the folder here. Okay. All right, so we've got lots of crypto stuff. Unidentified access. I don't know what that is, but maybe that's interesting. We have signal session cipher, which is presumably related. Signal service cipher. I don't know what the difference between the session and the service is. Session should be, if I'm understanding how they use session correctly, basically what we're doing is we have some set of long-lived keys. I'm going to guess an elliptic curve public-private key pair that essentially identifies each user. And then using those long-lived keys, we're going to generate session keys, sort of similar to how TLS does things. In TLS, each time you contact the server, you negotiate using Diffie-Hellman some session keys, and those are symmetric keys. And being symmetric keys, they're faster to encrypt and decrypt with, than the asymmetric keys, and they're also short-lived. So you throw them away at the end of the session. And so all of that is good for privacy as well. So I think that what we do is we continually renegotiate new session keys. And that's basically what the ratchet is up to. Profile cipher, I have no idea what profile cipher is. HMAC SIV, this should just basically be some HMAC. Then we have envelope, metadata, envelope, content. I'm not sure what those are, but we'll take a quick look at them just to kind of categorize what they're up to. And then we have attachment cipher. This is presumably for attachments, like when I send somebody an image or whatever, that attachment will be encrypted, and maybe for some reason that encryption is different. It's different from it has different requirements than encrypting small amounts of text. Okay, so this will be a good starting point, I think. Did we miss anything? Signal group cipher is probably interesting. Signal session cipher and session builder will presumably also be interesting. So let's take a look. Let's start here and see what we can see. So here we are in unidentified access, which is intriguingly named. We have an unidentified access key, which is just some list of bytes as opposed to like some crypto primitive. I think normally, if you have a key, it's better to not have just handle the raw bytes, but I'm not sure what this unidentified access thing is. So I'm not sure really what we're doing. We're going to derive access key from some profile key by creating a nonce and an input, but they start life as empty byte arrays. This is presumably creating an empty byte array in a way that's cryptographically secure. I don't know if there's any concern about leaking stuff for creating empty byte arrays. And then we're going to use AES GCM. GCM is a common AES mode, and that's going to be our cipher. And I'm not sure what we're using for. Are we using like Bouncy Castle? Or we're using JavaX crypto, I guess, for the crypto implementation, I think. And where were we? We're going to initialize the cipher. We're going to do encrypt as opposed to decrypt. And we've got some secret key specification, which says we're going to serialize the profile key, which will probably just produce a bunch of bytes. And we're going to interpret those bytes as an AES key. And then we're setting some GCM parameters. And then we're going to call cipher do final on the input, which will encrypt the input. What was the input? It started life as an empty array. Did it get changed into anything else? Can I close this panel on GitHub? Let me move this out of the way for a moment. It doesn't seem to have been turned into anything else. Maybe we're just encrypting the empty input and trimming the last 16 off the ciphertext, which should be, if I remember things correctly, basically just the HMAC. And we're going to look for errors. Why are we doing that? I have no idea. Will this tell us what this is? When sending to a story, I don't know what a story is. We always want to use sealed sender. Receivers will accept it for story messages. Oh, okay. So I think signal stories are kind of like these broadcast messages, maybe a little bit like trying to be like Snapchat, where you blast everyone in your list. However, there are some situations where we need to know if this access key will be correct for non-story purposes. So I'm guessing that this is somehow related to stories. But let me just try to do a search for unidentified access in Signal. If you get the error message, no, that's Windows. Sealed sender for Signal. In addition to end-to-end encryption that protects every Signal message, the Signal service is designed to minimize the data that is retained about Signal users. Yeah? By design, it does not record a record of your contacts, social graph, conversation list, location, user avatar, user profile name, group memberships, group titles, or group avatars. But what about identified? I'm not sure. I'm sure if we read all of this, we would find out what unidentified is, but let's just plow along and see. I don't think it's going to be fundamental. Okay, so here's Signal session cipher. This probably is more fundamental. This thread safe wrapper around session cipher. So we've got this Signal session cipher has a lock, which is maybe what they mean by thread safe. And it has a cipher, which is a session cipher. I don't know if we get to see. So we're importing session cipher from here. Can I open this? Can I do this? All right, well, screw that. All right, so we've got some cipher. I'm not sure exactly what it is. And we've just got encrypt and decrypt messages. These are padded messages. So I guess if you're, they have a certain fixed length. And if your message is less than that length, we just add stuff at the end. And we just lock stuff and then encrypt. And similarly to decrypt, we lock stuff and then decrypt the ciphertext. And these look like they're really generic methods. And then what is the difference between this decrypt and this decrypt? We have a pre-key signal message in one and a signal message in the other. Okay. And we have things like remote registration ID. So what I'm going to do, I'm going to try opening this stuff in Android Studio, which might give me a better interface to jumping around. So let's try this. Hopefully, now we can go to the definitions. There we go. Okay, so pre-key signal message implements ciphertext message and native handleguard.owner. What makes it pre-key? We've got some exceptions. Private key signal message, some unsafe handle stuff. I'm not sure what that means. We can get the identity key from the message, which we get by calling this native get identity key thing on a guard, and getting the native handle. So this looks like there's some native stuff in here. We can get the pre-key ID, getting signed pre-key ID. So I don't think this is telling us like what the pre-key is, but let's try just maybe a web search. Signal pre-key. We have this thing here. Maybe it's part of the Sesame algorithm. We'll publish one-time pre-keys and sign pre-keys to the server alongside their identity public keys. So we have the identity public key, and then we have these one-time pre-keys. And we also sign them. Sign them with what? Maybe with the identity key. To create an initiating session, a sending device will contact the server and fetch a pre-key bundle containing the recipient device's identity public key, signed pre-key, and a one-time pre-key, if one is available. These will be used by the DH is Diffie-Hellman. X3, I think this is some sort of three-time Diffie-Hellman algorithm to create a secret key that initializes a double ratchet session and an X3DH initial message. So the pre-key stuff is essentially like warming up the session. And the initial message is attached to every initiation message so that the recipient can use it to create a matching double ratchet session. And then once a response to an initiation message is received, the original sender ceases attaching the X3DH initial message to future messages, so the devices henceforth communicate only using the double ratchet. So this is used for Bootstrap. So since it's used for Bootstrap and it's a special case and they're uploaded to the server, there are going to be additional security situations, which I'm not going to read through, but I will add later. And but I think that's something to be cautious about, I guess. Yeah, okay. All right, so that's what's up with pre-keys. Let's go back to whatever this is called, Android Studio. Okay, so this is a special case, but the implementation is basically exactly the same. I think we acquire exactly the same lock, and we just call cipher decrypt. So at least at the level of signal session cipher, we're not doing anything differently. We do have this get remote registration ID, which is presumably also part of bootstrapping. We're going to get that from the cipher. So the cipher seems to have a bunch of stuff. So let's look at session cipher as a class. You've got a session store. I'm not sure if session store is a global or if it's just we just have maybe we just have a pointer to it or what. But returns a copy of the session record corresponding to the recipient ID plus device ID tuple. Okay, so the recipient, so each recipient might have multiple devices. For example, I might have 2 phones and a tablet and a computer, laptop, and I guess so I would have a single, presumably recipient ID and multiple device IDs, and together recipient and device would create a per recipient per device identifier, and the session record is defined at that level. Okay, that's fine for now. How do I go back? Yeah, here. Okay, so there's some session store that's stored in the session cipher, and we have the pre-key store, which is, I guess, also a storage thing, and the signed pre-key store, and these will store the pre-keys and the signed pre-keys, presumably. And whatever a Kyber key stores, I vaguely recall hearing Kyber, but I don't remember what it is. And also the identity key and the protocol address, the remote address, which is a signal protocol address, which we will open as well in a new tab. I think I can do just by doing that. Okay, and we'll look at that in a bit. That's stuff that's passed in, and then we just set those locally. So there's not really any mystery there. And I think that's really about it. So the session cipher is really just a collection of storage, it appears. And the session cipher can decrypt stuff. The first thing we try to do is native handle guard. I don't know what these handle guards are. I guess let's open this class as well. I don't think I can open it in the background, or at least maybe I don't know the key combination yet for that. We've got the remote address guard. I don't know if these are guards in the sense that they're going to like lock things, like prevent simultaneous usages, or if there's something else going on. And then after we try to guard some stuff, we call decrypt pre-key signal message, passing in all of the storage things. So passing in basically everything you need to figure out which key you're going to use to decrypt. So this is what? Decrypt the pre-key signal message. And similarly, we're going to have the same sort of stuff for the decrypt of the regular signal message. Get remote message ID, get remote registration ID. We're just going to get it from the session store load session on the remote address and call get remote registration ID. I'm just curious what this is actually going to do. This is going to peek into the guard and do that. And this is a native implementation. So I guess, do we bottom out here? Or does this mean that there's like C code here Public static native int. Yeah, I don't really remember enough about the native development kit, but maybe you can try searching for. No, we want to grep, right? Let's try this. We get a bunch of Java. Do we get any C? I don't think so. What about permutations of it? Like registration underscore ID. Okay, we get Kotlin. What about registration? I forget how wildcards work in grep. I don't remember if they're regexes or globs. And so let's just take this and grep for .c. We have .class. That's a Java thing. If we just do grep the Java. Then we have text files, XML files. Not sure. Maybe just one more thing. Let's try looking for things with the word native in it. Did I spell that correct? I think so. Okay, so we have .sos. We have these .class things. And I don't know what that means. We have libnative utils from JNI Labs. I don't know if this is a another repo. The JNI, yeah, okay. Well, I don't know. I'm not sure. Maybe we'll see later if we can figure out where those native stuff comes from. But at any rate, we kind of are bottoming out at native here. And that's fine. We've got native handle guard. Provides access to a Rust object handle. So are we using Rust? While keeping the Java wrapper alive. Intended for use with the try with resources syntax, native handle guard prevents the Java wrapper from being finalized, which would destroy the Rust object. Okay, so this is like guarding against garbage collection, it sounds like. So if the Java thing gets garbage collected, it sounds like then the Rust object goes away. But if you use this handle thing, it sticks around. To use it, the Java wrapper should conform to the native handle guard.owner interface. Note that it is not necessary to use native handle guard in the implementation of finalize itself. All right, so this native guard stuff is for Rust interop, which I wasn't even sure was aware was a thing. So let's take a look at signal Rust. Maybe this one? You have Signal Android, Signal Desktop, Signal Server, Java, Swift. Here's libsignal. Okay, so libsignal seems to be where the Rust is. Okay, that's cool. I just wanted to make sure it existed and was open source, so that we weren't like bottoming out at a essentially a closed binary. That's good enough for me. So here's signal protocol address. I don't remember where we saw this being used. Oh yeah, so this is going to tell us a little bit about how Signal decides where to send messages. Although I suspect that maybe we're going to bottom out at native stuff again. So we've got this native handle guard, and we're going to call this protocol address name. Similarly, we have a get service ID, which we're just going to parse from string by calling get name. What's get name? It's the thing we just looked at that's going to look in Rust. Okay. So far all the cool stuff is in Rust. That's fine. I wonder if the double ratchet stuff is really in Rust as well. So maybe let's take a quick peek at Rust. Got multiple languages. including crypto, device transfer, protocol. And this has AES mainly, and yeah, so protocol may be where the proto. You have things like address, constants, crypto, curve. Curve is, I'm going to guess, elliptic curve. Fingerprint, I'm going to guess, I don't think I've ever used fingerprints on Signal, but I guess they have support for it. And we have things like session and session cipher. And ratchet. So I guess let's look at these. I don't normally jump across repos, but it seems worth doing. And then in protocol, is that where we were before? This is different, right? That was just source. Here's source proto. Wire, I guess this is the wire protocol. We have a proto file, so they're using protocol buffers. Proto 2. And a signal message, a signal message has a ratchet key, a counter. I'm guessing the counter is for the ratchet to know how many clicks we've done. The previous counter, and a ciphertext. So every time you send a message, this is what you're sending. You're sending the ratchet where we are, where we were before. And then we have this pre-key signal message, which we saw a little bit about on that web page, which has things like the registration ID, and IDs for the pre-key and the signed pre-key and the Kyber. And what identity key is presumably the main asymmetric key that identifies you. I'm not sure what base key is, but some other kind of key that possibly serves as a base for other keys, and so on. The sender key message has a chain ID and iteration. I'm not sure how what chain is as distinct from the ratchet. But we have a distribution UUID as well, and a ciphertext. And okay. Then in libsignal, I'm going to guess this is not so important. We mainly have things like AES 256, encryption and decryption stuff. I saw some HMAC stuff. That's, I think, going to be relatively standard. Here's session cipher. And is this what we think is important? Let's take a look at what else we have. We have session. Session has things like process pre-key implementation, process key pre-key bundle, and session cipher has message decrypt. We have encrypt, decrypt message with something, get or create chain key, etc. Okay. I have a feeling that this is going to be more important. Here's ratchet. Let's look at ratchet first, I guess. And here's protocol.rs. Let's quickly look at protocol.rs. You've got this ciphertext message enum thing that has a signal message pre-key. It's one of these things. Plain text content. I'm not sure what plain text content is. And then we have message types. Whisper, I'm going to guess, is the default because this used to be called like Open Whisper or something along those lines. Pre-key is the pre-key message. Sender key, I'm not sure. And I don't know when we use plain text messages. Maybe to communicate with the server somehow, because the ciphertext has to go inside of something. Although presumably that's guarded by TLS as well. And then a ciphertext message. This is an implementation. I'm not a Rust person. I think that I'm going to guess the way that this works is that this is essentially saying that we're essentially implementing an interface, which is really the enum, right? And these are the methods that do it. And we're match, I'm going to guess, is just pattern matching. And we're kind of doing maybe some sort of dispatch. We're returning different message types depending on the type of the message. If it's a ciphertext message, signal message, then we're going to map that to a whisper, this other enum. All right. Here's a signal message struct, which has the public key as the sender ratchet key. You've got a counter, the previous counter. This is the same stuff that's in the proto. MAC length is 8, which I think is standard. we can create a new message, new signal message. Where we have to give it a MAC key, a message version, and the ratchet key and a counter, and presumably some plain text, right? Or no, we give it the ciphertext. So when we create the signal message, we've already encrypted, I guess. And we've got things to verify the MAC address. We can get the body, which just returns the ciphertext, etc. And it's computing the MAC address we saw verifying. This one is for computing. And that's all kind of like standard. Let's look at what signal Kyber is. Oh, sorry, I missed the message here. Does it create a TCP TLS socket with server to receive new messages or HTTPS? I'm not sure that I understand the question. I don't think we've seen the server I don't think we've seen any code yet that talks to the server, but I'm willing to bet that it uses TLS, which is the same as HTTPS. I'm not sure if you're asking whether they're different, or whether you're asking whether it's TCP in particular. But yeah, I would guess it's TCP, protected by TLS, and that is all I really know. Oh, maybe, so Kyber is maybe quantum resistant. Crystal's Kyber is built on solid foundations. Okay. Okay, so whatever Crystal's Kyber is, it seems to be some sort of quantum resistant algorithm. Cryptographic suite for algebraic lattices. Okay, so this is some lattice thing. Learning with errors, which I forget. I forget the details of how learning with errors works. I think it's basically a lattice, and you like do perturbations of the lattice, and that's how you come up with your encrypted message or something along those lines. Okay, so when I see Kyber, I'm just going to assume that that's going to be like next generation quantum stuff. All right, so here's ratchet, which I think is not what we just looked at. And the ratchet allows us to derive keys, which is good. We haven't yet pulled up the double. Let me spell signal correctly, even though it's behind this window. Let's pull up a visual of the double ratchet algorithm. Okay, so we have some KDF key. KDF is a key derivation function. It's going to eat some entropy and a key and produce and derive a key. So into the KDF, I guess, goes a KDF key and some input. And then out comes another KDF key and an output key. And I don't know what we do with that output key, but then we keep doing KDF. So I think this is like the KDF ratchet. That's one leg of the double ratchet. A KDF chain is a core concept in the double ratchet algorithm. We define a KDF as a cryptographic function that takes a secret and a random KDF key and some input data and returns output data. The output data is indistinguishable from random, so it's some PRF. So here's the KDF chain. When some of the output of the KDF is used as an output key and some is used to replace the KDF key. Okay, so we're going to generate, I don't know how many bytes, but let's say that half generates like twice as many bytes as we need for our use case. And I think our use case is just going to be negotiating a new session key, but I guess I'll read further. But half of that entropy essentially is going to be used for renegotiation, or what I think is probably renegotiation, and the other half is going to be used to keep the KDF key running, the KDF key crank ratchet thing running. And then we have the symmetric key ratchet. Every message is encrypted with a unique message key. The message keys are output keys from the sending and receiving KDF chains. Okay, so the output keys here, these are the things that go into making the symmetric key for encrypting messages. And so we've relabeled some stuff here. I'm guessing that chain key is the same as KDF key, and then input is the same thing as constant. I'm not sure. The KDF inputs for sending and receiving chains are constant, so these chains don't provide break and recovery. The sending and receiving chains just ensure that each message is encrypted with a unique key that can be deleted after encryption or decryption. Calculating the next chain key and message key from a given chain key is a single ratchet step in the symmetric key ratchet. Maybe this is a separate KDF chain. I'm not sure. And then we have a Diffie-Hellman ratchet. Is it the same? To prevent this, the double ratchet combines the symmetric key ratchet with a Diffie-Hellman ratchet, which updates the chain keys based on Diffie-Hellman outputs. To implement the DH ratchet, each party generates a DH key pair. So this is going to be a public key and private key, which become the current ratchet key pair. So these ratchet keys that we've seen in the code, they're going to change frequently. Each message from either party begins with a header, which contains the sender's current ratchet public key. I think that we've seen this in the protobuf messages, protobuf definition, I guess. When a ratchet public key is received from the remote party, a DH ratchet step is performed. So when you get the ratchet public key, you you crank the DH ratchet, and that replaces on your device the current ratchet key pair with a new key pair. And so the way Diffie-Hellman works, when we do this, even though we're receiving different data, we arrive at the same key so we can communicate. This results in ping-pong behavior as the parties take turns replacing ratchet key pairs. Okay, so I guess the first KDF stuff we saw was not part of the ratchet. The two ratchets are the Diffie-Hellman ratchet and the symmetric key ratchet, I guess. If I'm understanding correctly, which I may not. That's at least enough for us to have a little bit more context with the code. All right, so in ratchet.rs, we have this derived keys. Are we using Kyber, which I think is just quantum resistant stuff. That's just some Boolean. And whether we're using Kyber or not, we have secret input. We're going to return a root key and a chain key. And if we are using Kyber, we're going to use this Crystal's Kyber 1024 stuff. Otherwise, we're going to use, I guess, whisper text. And then we're going to derive keys, and then we're going to give it a label. And the label comes from where? From here, from whether or not we're using Kyber. All right. And then derive keys with label is presumably just going to do peek at the label maybe and decide what to do. So we're going to have this mutable secret stuff, which I don't know the syntax, but I'm guessing this is 64 zeros in an array. We initialize some KDF, some hash-based KDF based on SHA-256. And I guess maybe dump it into secrets. I'm not sure. And then we're going to split the secrets at the index 32. That's going to give us our root key bytes and the chain key bytes. And then we're going to call the root key and chain key constructors, essentially, it looks like, and create objects that have actual types as opposed to just being untyped byte arrays. And then we have Alice and Bob make it directly into the code. So I guess, I don't know whether we are Alice or Bob, but we have a RNG. I'm not sure what plus is. Maybe this is some sort of some type or type bound in Rust. If you know Rust, maybe let me know. And we're going to take some parameters. And we have a mutable CSPRNG. I don't know what CS is. Some kind of random number generator, though. And we look in the parameters at our identity key pair and get the identity key. We generate a new key with the what I assume is a cryptographically secure random number generator. That'll be the new sending ratchet key. Then we create this secrets vector, which is a vector now, as opposed to up here, it looked like this was maybe more of a traditional array. At any rate, we're creating, we're going to have, I guess, 5 lots of 32. And I don't know what this is, discontinuity bytes. We're going to do something with secrets to massage it. And then we're going to get our private key, the sender's private key, and do some stuff with it. We're going to call extend from slice with our identity key pair. So we're looking at our identity key, getting the private key, and calculating the agreement with their signed pre-key. So we're baking in the signed pre-key. I'm not sure what that is, and I'm not sure whether calculate agreement is doing Diffie-Hellman stuff or not. And then I guess extend from slice is maybe just adding to the end of the array. At any rate, we're doing more calculated agreement. Let's see if we can find it. So I'll open up calculate agreement in the background. And then we're doing more calculate agreement stuff with their public key and then with their signed pre-key. And I guess we're stuffing them all into a secrets vector. And doing something with their one-time pre-key, again, calling calculate agreement. And then we've got this Kyber ciphertext stuff, which I will just ignore. More Kyber stuff. Finally, we're calling derived keys, depending on whether you have Kyber on the secrets. So we're stuffing a bunch of stuff into secrets using this calculate agreement stuff. And then we're deriving keys with them, and that gives us a new root key and chain key. And then the sending, somehow we're going to modify them to get the sending chain key and the sending root key. And we do that by calling create chain on the root key with their ratchet key passed as one parameter. And the sending ratchet key, private key, passes the other. And I think the sending ratchet key is the new ratchet key, and then I guess this is the old ratchet key. Let's see if we can verify that the sending ratchet key is the one we just created. Yeah, it's newly generated in this function. Okay. So, and then we call session state new. We're creating a new session state with which may have Kyber, may not have. We're passing in our identity. We're sending their identity key as one of the arguments. We're sending the new chain root key, and we're sending our public key. And whatever this with receiver chain and with sender chain is doing. And then some possible Kyber stuff, and then saying okay. And then initialize Bob. So that's initialize Alice session. So I'm guessing Alice is when we control the creation of the new, the next step in the Diffie-Hellman ratchet. And then Bob should presumably be when they control the next step in the Diffie-Hellman ratchet. And so what I expect to see here is that instead of generating a new, wait, no, that's not it. Instead of generating a new ratchet key, we should be, I think, taking their ratchet key. And let's see if that's true. So we do more secret stuff. And we're getting our one-time pre-key pair. Were we using their one-time pre-key pair before? Their one-time pre-key pair. So we were using their stuff to stuff into secrets, it looks like. Now we're stuffing in our stuff, it looks like. Our versus their. And the end looks the same. I don't see where we get their base key, their identity key. We have this, maybe it's in parameters, but not the identity key. What did they call it up here? Sending ratchet key. I'm just going to do a quick scan to see if I see anything ratchet related. Okay, so at the very end, we send our ratchet key pair. or we do something with our ratchet key pair. But it seemed like the switch is that we've moved from stuffing the secrets full of our stuff versus their stuff. And I think that is the, if one is the ping, then the other, I think, is the pong of the ratchet. So I think that more or less checks out. I had opened some file here, right? This was calculate agreement. Yeah. So a lot of it's based on calculate agreement. I'm not sure what this is doing, but we're going to pass in some reference to ourselves, their public key, and we're going to get as a result, box. I'm going to guess it's just like a boxed type of U8, presumably uint8. And we're matching. I don't know the syntax. I'm going to guess that we're going to match on our key and their key. What happens if we don't match? I don't know. There doesn't seem to be any fallback. But we're calling DJB private key on their. Where did private key come from? Is private key our private key maybe? Or I'm not. I'll ask ChatGPT about what the syntax is doing. But we're doing some DGB crypto thing. So DGB is a famous crypto guy, and I assume that this is one of his algorithms. But we've got the private key and the public key that we're passing these into. I think this is defining like a lambda. So the lambda is going to take a private and a public key, and we're going to use curve 25519 and get the private key from whatever data that we passed into the private key variable. That's going to be our new private key. And then what we're returning is the private key. We're going to call calculate agreement from the private key. So let's see if we can figure out what this one does. This is what, line 275? Let's see if we can find where DJB private key is. It's some key that has for this. Yeah, I don't know. All right. Yeah, I'm not sure what calculate agreement is ultimately doing, but let's see if we can look up for DJB private key. So Dan Bernstein, I guess, is the guy, is the cryptographer I was thinking of. But maybe he's maybe like discovered or figured out this elliptic curve somehow. I'm not really sure. But let's see if we can also find signal calculate, or maybe calculate agreements here. Sorry, signal calculate agreement. Yeah, no, you don't want me to. Okay. There's a last, oops, not jump to line. Isn't that search? Calculate agreement. Let's just do a search. So maybe here. This seems like the same thing we were just looking at. This looks promising. All right, so calculate agreement is going to take self, which I think is a private key, and their public key. And we're going to call on self. We're going to, yeah. So calculate agreement is just Diffie-Hellman. Why is it called calculated agreement? I don't know. But the calculate agreement stuff is all just doing Diffie-Hellman. And so what we were seeing in those functions where we were just essentially doing the Diffie-Hellman ratchet with a strange name. Okay, that is kind of as expected. And then let's just take a look at message encrypt. Message encrypt in session cipher.rs. We're still in Rust. We're in libsignal instead of the signal Android. And it's going to take a plain text, p text, which I'm going to guess is plain text, and a protocol address, a session store, identity key store, and the system time. We're going to return a ciphertext message. And we're just going to essentially get the session record and make sure that it exists and whatnot. So we're going to call on the session state, we're going to get sender chain key. And we'll look at, on the chain key, we'll get the message keys. I guess the chain key is the keeper of the message keys. Then we're going to get the sender's ratchet key, which we call sender ephemeral. We're going to get the previous counter and the session version, all pretty logical. And then we're going to get our local identity key and their identity key. Local meaning ours, their meaning theirs. And we're going to set the variable ciphertext to the result of AES encrypting with CVC using the cipher key from message keys, which we got from the chain key. And I'm guessing this is actually a derivation. I said the chain key was the keeper of the message keys. I think this is really just deriving the message keys using the ratchets. And then I guess an IV, I'm not sure where the IV comes from. Presumably it's just random. And then that's the ciphertext. And then we just compose the message by essentially adding metadata, it looks like. So the only thing really to look at from an implementation standpoint is maybe this. Have we looked at message keys? So here's storage.proto. Message keys. We'll take a chain key, and so we're calling the key derivation function, passing in this thing, calculate base material with, this looks like an enum message key seed and some index. And this is just going to be the key derivation thing, which we saw before. It says SHA-256 based HKDF. And we take the input key material, essentially HKDF it, and then it looks like, where's OKM? It's, I guess, the key material, and then we're like dividing it up for the cipher key, the MAC key, and the IV. Okay, so that was all quite a detour from Signal Android, but I think that's good. At least we've seen what some of the crypto looks like. I was not totally happy with things like kind of like bottoming out at stuff we hadn't looked at. Maybe the last thing I want to look at in Rust. Are we still in Rust? No, let's see. I want to see at least where the code is that calls the server. I'm going to guess it's in Rust. Maybe it's not in Rust. Maybe it's in Android. Maybe net. Net seems promising. Lib proto env chat CDSI. We have more proto files. Yeah, like WebSocket. What are we WebSocketing to? Let's look at the proto files first. We've got some WebSocket messages like with things like verbs. So verbs going to be like put, get, kind of like the HTTP verbs, I assume. And I guess we're WebSocketing to the servers controlled by Signal. And I think the Signal server code is not open source, if I remember correctly, but maybe you can verify that. And this just basically looks like what an HTTP message would look like, except we're using WebSockets and protocol buffers. We've got things like headers, messages, statuses, all that sort of stuff. And then we have client requests. I still don't know what ACI is. I guess let's look that up. Oops. Some big endian stuff. A token, which allows rate limiting. So this is some kind of like server implementation. How about signal ACI? Sometimes the code says PNI or ACI, which are other pieces in building usernames. Adjacent channel interface. I'm not sure. Maybe if I add whisper. I'm not sure. I'm not going to really dig into what ACI. Maybe this will tell us. The PNI. How about ACI PNI signal? Recipient. With a full ACI PNI E164 tuple. Are these like phone things? I have no idea. Let's ask ChatGPT. Oops. In Signal, what are ACI, was it PNI and E something or other? E164. Access control interface, airports? No. Let's ask Bard. Used to uniquely address users on the platform. Account contact identifier, unique identifier assigned to each Signal account. It's a username. It's like a username, but not publicly visible and not linked to any phone number or personal information. It's an internal ID within Signal. PNI is phone number identifier. So I guess basically your phone number. Allows Signal to contact users with phone numbers, even if they haven't exchanged contact information. So this is like when you are inviting people to Signal or whatever, or maybe, yeah, I don't know. Then E164 is a standard international phone number format, including the country code and full phone number. ACI is primarily used for internal identification and linking between different devices. PNI enables phone number-based discovery and communication, even without prior contact exchange. And then E164 provides additional context and allows for easier recognition by users familiar with traditional phone numbers. Okay, so these are different identifiers for recipients. Very well. How long are we currently? We're at least an hour, right? An hour and 4. Almost an hour exactly. Move the chat off for a second. All right, so that's enough crypto for now. The crypto in Android bottomed out in native. We explored the native a little bit. But since, as I mentioned at the top of this stream, that this is our first Android thing, let's look a little bit at the UI. Okay. So I'm going to guess UI is largely in core UI. We'll see. Bottom sheets. We have things like buttons. Buttons and dialogues are good. Dividers, rows, and scaffolds. And texts. Is text like text messages? Let's see if text is interesting at all. For header row for settings pages. So in the settings page, this is some stuff. That's not so exciting. Rows. A row consisting of a radio button and text, which takes up the full width of the screen. So let's see if we can find a signal screenshot. So somebody was suggesting that I run the code. I'm on a VM here. Whoops. And if I try to run Android code, it's way too slow. So unfortunately, I'm not able to do that. But see if we can get a screenshot. Make sure it's from maybe the past year or so. Or tools. Went past year, but whatever. Okay, so this is the desktop. I think this is the mobile. How about this one? This is easier to see. Okay. So I'm not sure what the text is. I don't know if this is supposed to be for a message or for something else. It said it takes up the whole screen. Let's just open a few of these. Okay. And we've got a radio. Okay, so radio row is what it's called. It's got text, whether it's selected, modifier. I'm not sure what the modifier is, and label. Full max width, I'm guessing, is the thing that makes it take up the whole screen. We've got some default padding. We're going to align vertically. We'll align it in the center. And then we've got a radio button. I'm not actually familiar with the syntax, but this looks like standard, maybe like kind of like React style syntax, where we're just declaring kind of like we would in HTML. Like a row is nested inside of a radio row, and then a radio button is in the row, and then we've got a column. So that seems to be what's going on here. And then inside of the row, each row has a column. I don't know whether it's aligned vertically or horizontally yet, but the column has text with some theme, I guess material theme, since we're Android. And if the label is non-null, the column also has label. And I'm wondering whether this is for like the emoji support. I don't think it is. But if you are in a chat, I guess these are all, you would have something like that. You have a bunch of rows of text stuff, and the text stuff might also have like annotations on it, but I don't think that's what we're looking at yet. And we've got this toggle row thing, which is maybe a row you can toggle. It's composable, which again, I don't know. I don't know what that means, but we have whether it's checked. Oh, okay, so toggles is like in settings maybe. Yeah, I bet this is all setting stuff. Settings, signal, Android, settings screen. I don't know. I think in Android Studio, if I knew how to quickly pull up this file, we could visualize it in the XML, but I'm not sure it took me a while to try to remember how to find files in Android Studio. So this is just some toggle stuff, and we've got text and row and a thing, whether it's toggle or not, etc. Okay, so this is not so exciting, I think. That's rows. Buttons. We've got large content buttons, large primary, and some modifier stuff. This is all like layout. I think originally in earlier versions of Android, this would kind of all be XML, wouldn't it? It seems like we're defining the UI in code, as opposed to what I was intending to look at was the code that manipulates the UI. So let's see if we can find some of that. And maybe just for fun, we'll see if we can find it in Android Studio. So not in libsignal service, I don't think. Or UI. Actually, that was not so hard to find. I'm not going to build it. Let's get rid of this, get rid of whatever this is. I don't think I need this Gradle stuff. I'm not sure if I can visualize it. Can I visualize it? I'm not sure. Here's resources. That just has like string values. All right, whatever. Okay, so this is just buttons, large tonal. I'm not sure what a tonal button is. We've got things like we've had some on-click modifier, and whether the button is enabled, it's got some shape and some colors, you know, like UI stuff. And is that all? Is that all that's here in UI? Here's some themes. This and the signal theme. All right, so that's core UI. We have core util, donations, glide, web app, Gradle, image editor, libsignal, photo view, and paging. What's in paging? I'm going to guess this is paging of chat messages, maybe. We have an event lister and a main activity. Is this the, but the main activity is for paging test. That's not so exciting. But maybe now that I'm reminded, let's see if we can just find the main activity as an entry point. Do we have any? Nope. Okay, we've got a few main activities. Spinner test, context test, secure SMS. Yeah, okay, that's what we were looking for. So it's just called app is the folder I was looking at, which is such a generic name that I must have just glossed over it. Here we are. Main. Okay, so here's like maybe the main folder of all the Android non-crypto Android-y stuff. And I'm not sure how well this you can see this. We have things like animations, which is just for eye candy, audio, avatars, which is like the photo of you. Backup is presumably to support backing up. Signal does these like encrypted backups, and you can configure them. Contacts, contact share, crash, an entry point for crypto. The database is actually probably somewhat interesting. And the list of devices, emojis, emojis, I'm sure takes up a lot of stuff. Groups is like for group chats. Jobs is probably some sort of job queue. Keyboard, logging, main, I guess. Let's open this file. Maps, media, migrations, notifications, payments, preferences. I don't know what QR. Oh, QR is just like a QR code. Registration, reactions. Where are the chat messages? And we've got some WebRTC support for calling. Is this in a folder, this stuff? I think this is, let's try opening main fragment and main activity. But I didn't really see chat. Did we skip chat? Messages, I guess they're called. Message details, messages. Let's look at messages, I guess. And we're just going to do it quickly. We got to less UI stuff than I had intended, but that's okay because the stuff we looked at I think was important. So we have message state, call message processor, data message, maybe data message processor, message decryptor. No, I think we've seen enough crypto stuff. Story message. I'm going to ignore stories. Signal service proto util. I'm going to guess that's protocol stuff. A WebSocket drainer. And protocol. Buffer identity key store. This is like identity stuff. Let's take a look at these and then maybe call it a day. All right. Well, where shall we start? Main activity, host fragment. Is this main activity for the app or for something else? I'm not sure. Yeah, this is the main app, I guess. Okay. We'll just like quickly look at this. I don't think this is going to be especially super interesting. Database.proto. You want to see database.proto? We could take a look at that. Proto wire. Let me open up this. Main. I think we're in main here. App source. Main proto wire. Shouldn't there be a Java in there? Wait. No. Sure. I'll add database proto. I think we'll do that after the other stuff, though. Okay. So this is not the main activity, but it's the main activity host fragment. And we're going to inflate it from some XML layout. And where's XML? Here we go. Let's choose one of these mostly at random. Do we get a view of it? I think we do. I remember developing Android from several years ago. Okay, so we have this view of the XML defines kind of this screen, and Android will try to render it. And let's see if we can find the chat screen, which is maybe called conversation. Conversation item header. Conversation input panel. Conversation list tabs. Try that. This is really slow. I'm not really sure what we're looking at. This is some subset of a subset of. It looks like the conversation UI is kind of divided into 800 different XML files, and I'm not really sure which one is the like the entry point. So I'm not going to dig too deep. But here is one part of the UI, which is the main activity list host fragment, and we're doing kind of standard Android stuff with it. We've got this late init stuff because there are a bunch of variables that don't really make sense to initialize until your app has kind of been bootstrapped enough. And the way Android works is it has these like lifecycle entry points, like on view created. So when your view is created, you're going to like do some stuff like search for the appropriate XML for example, toolbar background and toolbar, and set those up and essentially create references to them. These are probably some of the late init stuff. Yeah, like toolbar background is late init. And you're going to set on the notification profile status, you're going to set an on-click listener, kind of wiring up things. And then we have this list of disposables, and we're going to add to it the conversation list tabs view model .state .subscribe by, and that's going to take some state. And when it gets that state, it's going to do some stuff. It's going to find some like UI fragment, I guess, namely the nav controller. And it's going to look at the destination, I guess, from the state. So I think when you like make a change, the way that they've set it up, presumably, is that the state will change and that will essentially emit an event. And we're kind of looking at maybe the what the event thinks the destination is. And if it's the conversation list fragment, then we're going to tell it to go to the conversation list. And if it's the conversation list archive fragment, then I guess we'll do nothing. And if it's stories, then we'll go to the stories thing and so on. This is kind of like not quite home rolled, but maybe like a more awkward version of the sort of pattern we saw in React and Flutter, where there's some state, and as the state changes, you have like essentially kind of like reducers that send you to the place you're supposed to go. And then go to state conversation list. We have the implementation here. We look at the tab. And if we are on chats, we do nothing. Otherwise, we do a bunch of stuff, including whatever camera fab is. We might do some stuff with the camera, I guess. I don't know if fab is fabricate or what. And do more navigation stuff. Okay, so this is all standard Android things. And then we, similarly to whatever we were just looking at, whether that was on create or I don't want this. But we have things like on resume. So when, I forget exactly when on resume is called, but maybe when your window goes in the background, it gets paused, I think. And then when it comes in the foreground, it becomes resumed, and you just have to wire up all of these lifecycle stuff. So that's just Android-y kind of like record keeping, essentially. Here's the paging test main activity, which we're going to thoroughly ignore. Here's the database protocol buffer, which was requested by get study learn op. And I have no idea what this is. This is, I guess, a protobuf for the database. I don't know if we're storing the protos or what. But we have a reaction list. So I'm guessing reaction is like the emoji. So you need to know what emoji is being used, who is the author, I guess, of the, I don't know if this is author of the original message or author of the reaction, and a sent time and a received time. And this is apparently deprecated. And you can have a list of reactions. We have badges. And the badges have identifiers, category, name, description, a URL for the image. I'm not sure how they store URLs. I don't know if this is like a URL on your file system, or I guess this is probably a URL in the Signal server. I'm not sure. If it's on the Signal server, I would expect that they only store the encrypted image so that the Signal people themselves can't see it. But I don't actually know where that code is, and I don't think we're going to have time to search for it. But the badge can have an expiration, whether it's visible, and whatever image density is. And you can have a bunch of badges. And then decrypted group v2 context. So this is something about, I'm guessing, group messages and decryption. We have a group state, a previous group state. Whether the group has changed, like maybe when you're adding or deleting people, and some context. And these are red, which I think means that I don't know, I don't have them. Is that right? Not sure. I guess Android Studio doesn't know where these things are defined. Some stuff about temporal auth credentials. Audio waveform data. This is, I think, for sending voice notes. It sends like an audio wave thing. This is details about profile changes. Body range list. This looks like text styles. Let's see. Bold, italic, spoiler, strike through. Spoiler is, I'm going to guess, covered up until you click on it. The rest, I think, are obvious. And a button, which has a label and an action, and certain like that. I'm guessing that this is essentially, maybe study op, learn op sent this because this is where like the data model for messages seems to be defined. And then we have things like crypto value, mobile. I think this is for sending some sort of like cryptocurrency, which they built into Signal at one point. I don't know if it's still there. Wallpaper is presumably just a background that you can set for chats. And you have chat colors, etc. Custom avatars, story post text. So it makes sense for all of this data model to be in protocol buffers. Certainly as a fan of protocol buffers, I support it. What I don't know is who's using, like where are they using database proto? And so maybe let's just do a grep. or things that include it. Crypto util and database protos util. Collection of extensions to make working with database protos cleaner. But do they, I guess you would generate the code from the database proto. And I don't know whether these are stored directly in the database. SQLite database extensions. I'm not sure. It's maybe kind of a rabbit hole, but at some point these protos are used for defining this. And I'm going to guess that however they've laid out the actual database, that this is essentially the source of truth that gets used. All right. Here's main activity. We looked at the main activity fragment. And in the main activity, we have a few different things. We have the theme shows up here. We have a main navigator. I don't remember navigators from when I was developing Android, which was a long time ago. But I'm going to guess this is kind of like lets you navigate or route different parts of the app. We have onCreate, which is going to be the real entry point. And we're going to call super onCreate. We're going to set the content view to main activity, and all of this sort of stuff. Can I go here? That should be the main activity XML. Let's see if it looks interesting at all. And then we've got a pre-draw listener, which I guess will listen to stuff before things are drawn. Use pre-draw listener to delay drawing frames till conversation list is ready. Okay, so we're going to wait until we have the conversation list and try to avoid drawing until we have it, I suppose. And setting up things like media controller, whatever proxies and group links are, call links, just kind of wiring up all of the stuff, setting up lifecycle stuff. Present vital state, battery saver dialog, debug logs, and debug logs for crash. They're still using intents, which I thought were like a little bit on the older side of Android, but maybe they're still fundamental. And then a lot of it is just more wiring up of all the things. So that's, we're going to mainly ignore that. Okay, so the main entry point XML doesn't look like anything, which is not so surprising because I think all of the interesting functionality is like modularized into, we saw like 1,000 different XML files. Here's some fragment, which I'm going to ignore. Here's message state.java. And this is, we've got some enum, and it's literally just this enum. And it has things like whether decrypted IK, I guess, is like, I guess, different from other things like invalid message if it was corrupted. No session. Not used, but can't remove due to serialization. Legacy message, duplicate message. So these are like error conditions for decryption. And here's data message processor, which is in Kotlin now instead of Java. And have we looked at this? I don't think so. So we've got this function process, which is going to take a context, envelope, and a bunch of stuff. Maybe we have looked at this. And this seems to be some dispatch thing. So we're going to do pattern matching. And if the message is invalid, we're going to handle invalid message, etc. So this is just setting up a bunch of handlers. Checking if the, okay, so if we're down here, if we pass this handler, this is the same function, right? I guess if we're down here, then we're going to do some other stuff. We're going to make sure the group ID is not empty. And this looks like just error conditions for whether if the group is unknown. These may all just be error conditions at the end. I'm not sure. So is invalid, is end session, is expiration, is story reaction, is reaction, as remote delete, is payment, etc. If body is non-null, then we go to handle text message. Let's look at handle text message. This should be hopefully pretty straightforward. All right, so we get the body. We handle possible expiration events. So I think this is things like if you send a password or something, you can say you want it to disappear in a day or so, I think is possibly what the expiration is for. Notify typing stops from incoming message. That is when you're typing, a lot of chat systems do this. You'll get like ... as someone is typing, and I guess it'll stop doing ... when they stop typing. We're going to declare a text message from this incoming message constructor using a bunch of stuff that was passed into this function. And then we are going to, the very first thing we try to do is we look at the Signal database, the message is there, and try to insert the message into the inbox. And we get an insert result and possibly do some metrics. And if the insert result is non-null, then we're going to return we're going to get the message notifier from application dependencies, which is kind of as I mentioned before, this is just some way of kind of getting globals, it looks like. So we're going to get some message notifier and tell it that we've got a new notification. We're essentially just emitting an event. And we pass it the context, which is, I think, probably passed to us. Yeah, the first argument to this function. And we've got, we're going to set what the conversation ID is so that the UI can update that conversation, I guess, to pop up the new message. And whatever this message ID insert result message ID is, I guess this is maybe just setting the message ID. What's the return value here? The return value is a possibly null message ID. So this is the return here, I think. Okay. So that's what, that makes a lot of sense. But since we have access to the database here, let's just dive in and see if we can find out what this is doing. Actually, let's look at maybe Signal database. We've got a name, which is signal.db, and I think we're using SQLite. I saw it in the code, and I've seen it before when I was poking around on Signal. Okay, so Signal database.kt. What I would like to see if we can get to a description of the database itself, and maybe that's not the easiest thing to do. What are we importing? We've got the SQLite. No, imports are up here. SQLite helper stuff, logging, more database helpers, sync jobs, message table. We have a bunch of different tables, it looks like. Okay, db exec SQL message table create table. Let's look there. This seems to be I don't know what that is doing. Here's the create statement for the message, the table of messages, the table of chat messages. And I'm getting a request to do Chromium source code. I'll look at Chromium again at some point. I looked at it long ago when I was just starting all this stuff. I don't think I necessarily said anything especially insightful about it, but I would like to go back and look at Chromium and Firefox and whatnot. I have a bunch of requests though, so I'm trying to figure out how I want to process the existing requests and process new requests as well, because I don't want to just be totally have such a huge backlog that I'm not able to respond quickly to anything. So I'm still figuring that out. But your request for Chromium is noted. All right, so create table. We've got an ID. The data was sent, the thread ID. So it doesn't look like we're using we're not like just sticking in protos, which is, I would have been a little bit surprised if we were. But for example, we're writing the body as a text blob. And we're writing a bunch of metadata like when it expires. I don't know what quote ID is or body ranges or whatever. Okay. And then we're creating a bunch of indexes, as you might expect. So this is all as you would expect. And then I think that's all I wanted to see in the database, just to kind of see what it looked like. And do I want to look at insert message inbox? Not really. Cool. So I'm going to leave it there. Where we were about an hour and 40 minutes in. So Signal Android is humongous. I guess I didn't appreciate as a user of Signal just how humongous it is. But a lot of it, the Android stuff looks like maybe it is a mix of possibly like older Android styles and newer Android styles. We've got some Kotlin. We've also got some Java. I don't know if they're like really bought into any particular Android framework for handling streams or whatever. It kind of looks like they're doing a lot of stuff using pretty stock Java and Kotlin rather than like relying heavily on some like reactive library, for example. But the code is nice to read. It's easy to understand as far as Java goes. And then we also spend a lot of time looking into the Rust code for, it's a different repo, but also by the Signal people for the, I think libsignal is what it's called, that actually implements the cryptography. And I guess the idea there is that the native implementation is one, probably more able to do higher performance, and two, easier to share across across Android and iOS and iPad OS, which I think is possibly its own thing, and also the desktop implementation of Signal. So it makes sense to take that out and put that into Rust. And then I would also venture that Rust makes sense as opposed to C or C++ because you may get some safety benefits from Rust's kind of default safe way of doing things as opposed to C and C++, which are kind of like default default unsafe pointers and all that stuff. So that's Signal Android. Hope that was cool. Hope that was interesting. And I'll see you again next week. Not quite sure yet what I'll look at, but I'm going to try to put up a schedule more ahead of time now that my own schedule is starting to stabilize more than it was for the past few months. That's all for me. Thanks for watching.